Okay, so the first question was, for the review, will you guys have a handout? Yes, you will have a handout. I am finishing it up today, and then I'm going to send it to Katrina, and we're going to just like approve it together, go over it tonight, and then I will send it out tomorrow morning, probably. Also, here, let me just remind you guys while I have you here. So today is Monday, December 7th. Your exam is either the 10th or the 11th, depending on which section you are part of. Wednesday, December 9th is Up All Night, and that's when we all have our final exam reviews. Mine will be from 3 to 5 p.m. Katrina's will be from 7 to 9. And then in between those times, there will be tutoring available. I will be holding tutoring hours tomorrow, December 8th, and Wednesday, December 9th. I will send an email about that to you guys today. I just wanted to make sure I didn't send it too early so you guys forgot about it. I will be holding hours from 12 to 2 on both days, and it is a drop-in, so I will send you guys the link so you will be able to just drop into the session. You don't have to make an appointment or anything. You can just show up. So that's really cool. Yeah, there's a lot of material though. So if you guys have, like, if you guys want to come and review, I suggest like bringing either specific questions or specific topics that you guys want to cover, things like that, just so I can like best help you. And then just to reiterate, that is Tuesday, December 8th and Wednesday, December 9th from 12 to 1 p.m. They will be recorded, and I will be posting them, yes. And again, I'll send you guys an email later today to remind you about that and give you all the details. In addition to that, I had another announcement that I wanted to make, but it slipped my mind. So I'll just make it whenever it comes back to my head. And I'm sending the attendance sheet right now, so please sign in when you get a chance. And I'm going to see what other... Oh, yes. Okay, that's what I wanted to say. So I got a bunch of emails asking about handouts, answer keys, things like that. So I will send you guys an email with all the handouts from the semester, but they will be blank. I do not have answer keys filled out. The reason for that is because all of the handouts were filled out completely in SI sessions or in the videos that have been posted. So they are online. In addition, you guys can talk to each other if you want to, like if anyone doesn't have the answer to something. I know you guys are all really nice, so I don't think anyone would have a huge problem with it. Yeah, so I'm not sending out answer keys. The little cheat sheet things I do, I believe only chapter 18 doesn't have a cheat sheet. So I will be making one of those, and I will put all of them together and send it to you guys as one document, but I'm not going to add a bunch of stuff for all the chapters. So it's going to be all the cheat sheets you guys already have, plus chapter 18, all built into one document, and I will send that out. I've gotten a bunch of emails, and I will respond to those emails, but I just wanted to make a general announcement to everyone about that. Any questions? Comments, concerns? I saw a couple like topic suggestions, so I am keeping that in mind. But if I missed a question or anything, let me know. I think I answered all of them. Alrighty. So I'm sure by now you guys have seen the breakdown for the exam, right? Like how many questions will be from each chapter, things like that. If not, I wanted to really quickly go over it with you guys. So, okay, a couple people said they haven't seen it, so let me just open it up, actually. It's... Oh, Katrina's here. I love her. Hi. And I know Jared's here, too. My favorite Orgo people. Okay, so this is the breakdown. I think Dr. West posted it on Canvas for you guys. I think it's under, like, the exam reviews tab. So basically, as you guys can see, the breakdown is a little bit off from what I expected it to be. There's a lot of chapter 18. There's like almost double what there is for every other chapter. So for sure, when you're studying put a lot of focus into chapter 18, but there is a lot of questions on chapter 9, 11, 12, which was a long time ago. So don't just like completely forget about that stuff. So Katrina and I decided for the exam review, I'm going to do chapters 9, 11, 12, and 13, and chapter 18. And then she's going to do 14, 15, 16, 17, plus 18. So we're going to try to hit 18 as hard as we can, just so you guys get those bulk of points. So that being said, today I thought we could go back into the what to study guide that I sent you guys and kind of fill out the big important things together so that you guys know kind of what to focus on, what reactions there are, comparing and contrasting, that kind of stuff. And that should cover most of the questions you guys had in the chat. So unless there are any objections, I say let's get started. Someone asked a really great question, though. It's how fair is this exam? So I kind of read it wrong, but basically, like, how fair is this exam? So I think it's a fairly okay exam. Like, I think all of the Orgo 2 exams are like pretty fair, and they're like medium level difficulty. So like maybe a 5 out of 10 difficulty, because they are pretty straightforward. I think the final is a little bit harder than that, so maybe like a 7 or 8, just because it is so much material and it's easy to get tripped up. But I think the questions themselves are pretty fair. There's just a couple that are like weirdly worded and stuff, like the theoretically questions and stuff like that. But I try to give you guys hints for that as much as I can. Does he repeat questions? From what I've seen in the past, he does usually repeat a few. So let's go here. All right. So you guys can keep asking questions in the chat. I will look at that as we go. But so let's start with chunk number 1. So when we're talking about carbonyls, the first thing we learned is oxidation and reduction. So as I'm going through, I want you guys to take these reactions and put them kind of like in a table. And so oxidation was going from what to what, functional group wise? So in an oxidation reaction, what functional group goes to what functional group? Yes, okay. So we're usually going to start with an alcohol. And in this case, I'm going to give you a primary alcohol, just as the example. So we can have our oxidizing reagent, and I'm going to just put O here because we can pick from a bunch. And a primary alcohol can turn into an aldehyde, and then it can eventually turn into a carboxylic acid. So this is the general structure of an oxidation, right? What was the rule for knowing a strong oxidizing agent? So what was that little trick we used for recognizing strong oxidizing agents? 4 more oxygens, exactly. So when we're talking about reagents, we know strong equals 4 or more oxygens. And what was weak? There was DMSO, but there was another one. There was Sweary's reagent, but what was the most important one we talked about? PCC, exactly. That's Dr. West's favorite. There also is DMSO. DMSO4, though. Okay, cool. And then what about tertiary alcohols? Can we oxidize a tertiary alcohol? No. Perfect. Sweet. Awesome. Okay. What about... You know what? That's it. Okay. So reduction, we know, is going to be the opposite. So I'm going to pretty much draw the exact opposite of what I have here. We can start with a carboxylic acid. And when we have a reducing agent, what is the reducing species? So what is the nucleophile? H minus, perfect, okay. So we have our H minus, it eventually goes to the aldehyde, which then eventually goes to an alcohol, right? And so when we talk about group 1 and group 2, which one of those is more reactive? So less stable, more reactive. Yes, group 1. And so we know that that means group 2 must be more stable and less reactive. So which reagent works only with group 1? NaBH4, sweet. Okay, so I'm going to say only group 1. What about LiAlH4? It does work for group 2, but more importantly, it works for both of them. Exactly. So sorry, I'm like so zoomed in. I'm trying to like have decent handwriting. So yes, LiAlH4 works for both groups. And we have one other reagent. Do you guys remember what it is? Diba, exactly. And as you guys said, it goes from the ester to the aldehyde, or carboxylic acid to aldehyde. So I'm going to draw it, or I'm going to write it over here. Only works with group 2 and stops at aldehyde. Sweet. So that is pretty much my summary of carbonyls. So oxidation and reduction. If you know what's on this page, you should be fairly solid with oxidation and reduction. Any questions? So I'm gonna go here. All right, now we have our Grignards. And we know that we need what to make a Grignard? Yes, I can go back up. Just give me 1 second to write this. Okay, so in order to make the Grignard reagent, we are eventually going to make MgBr. But what kind of starting material are we going to use? Alkyl halide, exactly. So any kind of alkyl halide, let's say something like this. And we are going to react it with Mg and ether. And eventually we get that. So this is how we make the Grignard reagent. And I'm going to go back up for 1 second while we talk about this. So the Grignard reagent is a carbon with a minus sign, which means a negative charge. So it must be a strong what or what? Nucleophile or base. Sweet. Okay, so I'm going to go back down. So we know that it is a strong nucleophile and base. So we know that since the Grignard reagent can be a nucleophile and a base, when will the Grignard reagent or the Grignard reaction not happen? With an acidic hydrogen, exactly. So remind me a couple examples of an acidic hydrogen in this case. We have triple bonds, heteroatoms such as OH, yes, and a carboxylic acid, perfect. You guys are so good, I'm gonna cry. Okay, awesome. So let's zoom out a little bit. And I want you guys to practice the mechanism, obviously, but I'm going to draw you like a very basic, simplified version. So essentially, we're saying that we already made the Grignard reagent. So let's use that same one. And what are we going to use in the Grignard reaction? What'll be our electrophile? And then someone asked a question, which was, so this will only operate under base catalyzed conditions. So not necessarily. We usually want to have an acid along with our Grignard reagent, or like water, usually water. And we usually put it in as a second step. So like we'll do the Grignard reaction and then add water or something. And that's just used to protonate at the end. So yes, for our electrophile, we can use any carbonyl really. I'm going to show you with a carboxylic acid. So the fun part of a Grignard reagent is we're going to always attack at least once, right? But when we have a leaving group, we're essentially just going to replace that leaving group and reform our carbonyls. So what happens if we reform the carbonyl and kick off a leaving group? What do y'all think? What happens when we do the Grignard reaction one time and we're able to kick off the leaving group and reform the double bond? Exactly, we're going to attack again. And someone said in the comments or in the chat that sometimes this can work with epoxides, and yes, we have seen it a couple times where the Grignard reagent was used to open up an epoxide, so I'm glad you mentioned that. All right, so we're going to attack again, and now we can no longer reform the double bond because we don't have any more leaving groups. So what happens to that carbonyl? What does it turn into? An OH, exactly. And I'm going to rewrite that H2O here just so we remember that we can protonate this at the end. So that's the basis of the Grignard reagent and the Grignard reaction. One thing he really likes to show you guys sometimes is, I'm going to write it in purple. If he shows you like this, and he says PBr3, and then like A, and then after that Mg, ether, B. We know that PBr3 turns OH into bromine, and then the magnesium is going to turn that into the Grignard reagent. So all we're doing here is forming the Grignard reagent. I did that a little bit fast, but we've seen this a couple times. I just wanted to draw it here for you. It's one of those multi-step things. Any questions so far? Okay, cool. So moving.
I have a quick question.
Yes, please go ahead.
Was the negative charge on the end carbon or the one
For here?
in front of the carbon? Yeah. Is it at the very end?
Yes. So it's this. Okay. So what had happened was that wasn't actually supposed to be there. I just missed my pen a little bit. But I'm glad you pointed that out.
Okay. Thank you.
You're very welcome. Okay.
I'm sorry. What did you say that Mg ether did in that case, the multi-step reaction?
Okay, great question. So essentially, it's kind of like a longer way to make the Grignard reagent. So he'll start with this to fool you, and you make an alkyl halide in step 1, and you make A, and then Mg and ether will react with the alkyl halide to make the Grignard reagent. So anytime you see Mg, you're making the Grignard reagent. And if you see MgBr, you already have the Grignard reagent. Make sense?
Yes, thank you.
Okay. So when we go into chapter 16, we can kind of see a lot of similarities and differences with what we did kind of in chapters 11 and 12. So we're still doing carbonyl chemistry, but now we're doing nucleophilic additions, and there are a bunch of different reactions in chapter 16. So I'm not going to redraw them all now, but we can go back and look at the summary if you guys want to kind of go through them one by one. But the general stuff I want you to remember for chapter 16 is the reactions are reversible. So they're all at equilibrium. Some of them have differences between acid and base catalysts. So what reaction is different when you use acid versus when you use base? The acetal-ketol reaction, exactly. And I know someone unmuted. Did you have a question? No? Okay, sorry to call you out. I just didn't want to like accidentally skip you. Okay, so for the acetal and ketol reaction, we know that in acid catalyst, we're going to go all the way and make the final product. If we have a base catalyst or no catalyst at all, where do we end the reaction? What intermediate are we stuck with? The hemi, exactly, perfect. So many people answered, I'm so proud. And then someone had asked, do we need to know which is favored? Do you mean for like the acid and base catalyst? At equilibrium. Okay, great question. So at equilibrium, we will sometimes have like one reaction favored over the other. So just know that in the acetal-ketol reaction, we kind of prefer the starting material. We prefer the ketone. Same thing in the gem-diol reaction. We're actually going to prefer the ketone form over the gem-diol form. But we prefer the gem-diol over the aldehyde. So that's the only one you really need to remember. And I can repeat that. So the gem-diol reaction, you're going to favor the ketone form over the gem-diol form. And you're going to prefer the gem-diol form over the aldehyde form. And then someone asked me to repeat what I said about acids and bases. So in the acetal-ketol reaction, when we have an acid catalyst, we are going to end up making the acetal or the ketol. We're going to go all the way. And if we have a base catalyst or no catalyst at all, we're actually going to stop at the hemi. So we're only going to go to the middle. We're not going to go all the way to the final product. Cool?
So I have a quick question.
Yes.
How should we study this chapter? Because I feel like the handout was nothing we like went over. Like I feel like his handout that his practice problems were extremely hard.
For chapter 16 or like in general?
Yeah, chapter 16.
And you're talking about like the practice exam? Or like his practice problems like in the Canvas? Sorry, I like kind of zoned out a little bit. I didn't mean to.
Sorry, it wasn't letting me unmute. Yeah, the practice problems that he put on Canvas.
So as far as his practice problems go, I'm glad you mentioned that because a lot of people kind of emailed me in a panic saying that like they were insane and they like couldn't answer any of them. So please remember the chapter 16 practice problems that are posted have a lot of questions of reactions that we never did. So it eliminates like half of the questions in your packet. But if you see a question that we did not cover, so like there's reagents that we didn't cover, don't do it. Because that you won't be expected to know that. You won't be tested on that. Other than that, was that like the biggest issue you were finding? Okay, cool. And so yeah, as Katrina just said in the chat, the questions that are really good to do for practice, we covered those in the last exam review. So we highly recommend you watching those on the YouTube recording, just so you know like which ones you're expected to know and which ones you're not really expected to know. So the Wittig reaction. So the Wittig reaction is the only one in chapter 16 that is not going to be reversible. And can anyone tell me why they think it is not reversible? We actually didn't say this explicitly, but I want to see if you guys might know. One person said because the alkene is more stable. So that's a good thought process. That's one of the reasons. But a lot of the final products are better than the starting material, or like more stable. So there's actually a better answer. We can't break the double bond that forms, is what one person said. So why not? Because we break a lot of carbonyl double bonds. What's the difference? And while you answer, I mean, you're right. I just want to know your reasoning behind it. So I hope I didn't scare you. So, okay. So it does have to do with not being able to break the double bond. And as she said, it is because this is a carbon-carbon double bond. It's no longer between a carbon and a heteroatom. So that is absolutely right. So let's remember that the Wittig reaction is when we have a carbonyl and our PPH3. And we're going to do this the rosemary way. So let's just say we have these random, sure, whatever. Right? Okay, so we are Dr. Frankenstein now. We're going to cut off the heads, goodbye. Cut off the heads, goodbye. We're going to glue the two heads together and throw them away because we don't care. And then now we have the arms and legs. So we have to make sure we keep the arms on the same side. And we have to make sure we keep the legs on the same side. Does it matter how I orient the arms and how I orient the legs, as long as the arms stay on one side and the legs stay on the other side? No, exactly. So remember, as long as arms stay here and legs stay here, you can flip-flop them any way you want. Doesn't matter. Of course, there's going to be a more and less stable way to do it, but you guys don't really have to know that. You're not expected to know that. So before we move on, what is this thing called? Please remind me. Hint, it's on the screen. The ylid, exactly. So in order to make the ylid, we are going to start with what? Yes, so we're going to start with an alkyl halide again, as always, right? We react it with PPH3, and then we react it with base. And we end up making the ylid. So this is the basics of the Wittig reaction. Pretty much all you really need to know, as long as you know the rosemary way to go forwards, and then you can follow this logic to kind of go backwards as we did in the practice problems for the last exam. You should be golden for this one. Any questions whatsoever? If you do, as always, go ahead and ask, but I'm just going to scroll. So the second to last chapter for chunk number 1 is chapter 17, which is nucleophilic substitution. So this is where it tends to get a little bit tricky. So students are okay with all this carbonyl chemistry up until we add 17 and 18 in the mix because now things start kind of looking similar and you don't know what to do. So the biggest hint, or like the biggest way to remember things, is chapter 16, we added things and we did not have a leaving group. So we're working with aldehydes and ketones only. In chapter 17, we're working with carboxylic acid derivatives only because we have a leaving group and we replace it with the nucleophile. So we went over reactivity and naming esters. Obviously go over that. That's probably going to be like an easy couple of points. The only thing I want to make sure you guys remember is what is the most reactive carboxylic acid derivative? So the most reactive one that we went over. Yes, exactly. So the acid chloride or the acyl chloride, or you know what, I should just call it an acid halide because it can be any of the halogens. So the acid halide is going to be the most reactive. Can we form an acid halide through nucleophilic substitution? No! How do we make an acid chloride? Yes, perfect. So I'll add that here. I'll do it under here. We can use SOCl3, PBr3, PCl3, PCl5, so on and so forth. All of those reagents that we used in chapter 11 as protecting groups. Awesome. Alrighty. So the basis of a chapter 17 mechanism, I'll draw out right here for you. So we're going to have a leaving group, and we're going to react that with a nucleophile and some kind of catalyst. For chapter 18, it can pretty much be acid or base. It's pretty interchangeable. And all we end up doing is replacing the leaving group with our nucleophile. That's all it is for this chapter. As far as lactones and lactams go, please tell me, what is a lactone? What kind of functional group? One person said it, but I want a couple more. Yes, it's a cyclic ester. Perfect. And so what is a lactam? Cyclic amide. Sweet. And so we name those with the Greek alphabet, right? So someone please remind me, what is the order? We know we start with alpha, and then it goes what? Alpha, beta, gamma, delta. So that is our order. Sweet. So just as a reminder, when we are trying to name a lactone or a lactam, we're going to start at the alpha carbon because we know the alpha carbon is always the one adjacent to the carbonyl carbon. And then we go beta, gamma, delta, and we always name with the highest letter. So this is a question you guys might get. Which lactam is the most stable? Alpha, beta, gamma, or delta? What do you think? I want a couple more people, please. Because so far we got a couple different answers. So a couple people said delta, and that is correct. And the reason the delta lactone or delta lactam is most stable is because it is a 6-membered ring. So remember, 6-membered rings are going to be pretty much the most stable ones. Cyclohexanes in general are super, super stable. So anything with 6 members is going to be preferred. The least stable one would then be what? Which lactone is least stable? Yes, the triangle, but that's called alpha. Exactly. So alpha sucks. We don't like it. All righty. So that's pretty much it for that. So I know someone had questions about the lactones and lactams. So if you want to ask that one more time, please, and we can go over that now, that would be awesome.
Yeah, I did. It was how do we know when we're making and breaking lactones or lactams, or if we're actually doing like the nucleophilic acyl substitution?
Okay, that's a great question. So here, let me make a new page. Clear. All right. So making and breaking lactones. We can actually do it in a bunch of different ways. And I'm writing lactones, but the same rule applies for lactams as well. So when we're making lactones, we're pretty much going to start with something like this, right? And we're going to have what kind of catalyst? What do you think? And that's a good point. This is chapter 17, lactones. We want not a nucleophile and not an acid. Well, that kind of gives away, then it's a base. But let's think about this, right? So we want to make a lactone, right? And so in order to make this a better nucleophile, what kind of catalyst do we want? A base, right? We want to take away that hydrogen. We can use acid, but base is preferred. So let's say we have NaOH. Na is just a spectator, so we're going to not even draw it in. We don't care about it. So we're going to steal that hydrogen, right? And we end up, I'll draw the next step just so it's not ugly. At this point, we have made a negative charge on this oxygen, right? So what is our next step? What do we do with this negatively charged oxygen? Intramolecular attack. Yes, exactly. I'm so proud. So yes, we are going to attack right here. And so what's going to happen to the carboxylic acid? Yes, so we're going to have a leaving group leave and we're going to form a ring. Exactly. So our final product will be, let's not forget our carbons. So let's go ahead and count. 1, 2, 3. And I know oxygen will be inside the ring, so I'm going to count that. So let's go ahead and draw our 4-membered ring. And we know that on carbon number 3, we have a methyl. So let's not forget that. All right. So this would be our final product, right? And we know that this is a reaction that we use to make a lactone, right? But if we look at this from a different lens, this was a what? Or you know what, let me just, yeah, this is fine. A leaving group. And this was a what? The oxygen. Was a nucleophile. And what happened to that oxygen? Or, just kidding. What happened to that hydrogen? We just threw it away. It left. Ew, goodbye. So this, it got snatched, literally. So this looks very, very similar to our nucleophilic. What kind of reactions? Acyl substitutions, exactly. So even though the making and breaking new lactones looks like its own thing, it looks different and new, it's actually the same exact mechanism. It just kind of looks different. So all of the making and breaking lactones is actually going to be nucleophilic acyl substitutions.
So could we use your shortcut method in this instance?
Mm-hmm. Definitely. The only thing I say is don't forget to count the carbons in your ring. That's the biggest thing. And someone had asked a question and I lost it. So if I didn't answer your question, please ask it again. And someone asked a really great question about numbering. So do we always start counting from the carbonyl carbon? No, you don't have to, because we're not using like IUPAC numbering or anything. I just use an arbitrary numbering system to make sure I have the right number of carbons in my final product. I like to start at the carbonyl carbon, just because it makes sense to me. I don't know. And yes, okay. So the question was, could you explain why base catalyst was preferred over acid catalyst? Yes, I can. So in an acid catalyst, first of all, what do acid catalysts do? How do they catalyze the reaction? They make the electrophile more electrophilic. Exactly. So acid catalysts protonate the carbonyl, and then the reaction goes so on and so forth. So it takes more steps, and they're pretty much equal, but I prefer to draw it that way because it is slightly more favorable since you just go ahead and make this a good nucleophile and go on with the reaction. Cool. So chapter 18 is the big chunk, I guess, for this exam. So tautomerization. We know that tautomerization is different than just regular old moving around electrons, right? So what is a tautomerization? And how is it different from resonance? What do y'all think? Ooh, this is a really good one. So constitutional constitutional isomers converted through acid and base. So yes, that's like a perfect answer. We can also say that in a tautomerization, we're essentially picking up a hydrogen and moving it. So that's different than resonance because resonance only moves electrons while tautomerization moves hydrogens. And as someone in the chat said, it's different from resonance because bonds are being moved. Exactly. So you're making and breaking bonds. You're not just moving around electrons. So that is perfect. So for racimization, racimization is essentially just like a specific type of tautomerization. And so why do we call it a racimization? What do we need in order to do a racimization? Yes, exactly. So it forms a racemic mixture, so 50-50 RNS. And also I'm going to send you guys the attendance sheet one more time because this session's almost over. And we require a chiral alpha carbon with what? What's special about the chiral alpha carbon? What do we need? An alpha hydrogen. Perfect. All right. So as far as the reactions go, the big things I want you guys to remember is halogenation, acid versus base does matter. So with an acid catalyst, we can only do reaction one time. How many times can we do the reaction with a base catalyst? Someone said 2, which yes, that's true. But even more than that, we can do it all the way to completion. Exactly. So that's why we have the haloform reaction. So in base we replace all H's on more, or I'll say most. And that's why in the haloform reaction, we are going to substitute all 3 hydrogens. And someone asked, do you need excess base and halogen present to have multiple halogenations? So for the haloform reaction, since you're doing it 3 times, he will usually give you excess base and halogen. If you're only going to do it twice, he doesn't usually say excess. So sometimes he will give you excess, but you're kind of just expected to know. Basically, yeah. You're welcome. So the Hels-Volhard-Zielinski reaction, besides having an obnoxious name, is important because if you have H2O, you replace whatever halogen you put in there, and you end up with a carboxylic acid. If you don't have H2O, you end up with 2 bromines on your final product. So yes, awesome. Someone said it. We have either PBr3, Br2, and water, or PBr3 and Br2. So in either case, you end up with something like this. If you don't have water, you end up with a bromine here. If you do have water, you end up with a carboxylic acid. And yes, I can definitely repeat that. So if we have H2O, we end up with an OH here. If we do not have H2O, we end up with a halogen here. Cool. So for an alkylation, I'm not going to draw it, but you basically just end up adding whatever. You know what? I will give you the reagents. So we're going to start out with a base, and usually we use OET. So it looks something like that, right? And then what are we going to use next? What goes under the arrow? This has been the answer for like 4 questions today. Not H2O, we're actually going to use some carbon chain with a leaving group, and usually that leaving group will be a halogen, so we want an alkyl halide. And all we end up doing is adding the alkyl group, excuse me, to the alpha carbon. So for the last 3, I don't have enough space to like draw them out here, and we're running out of time. So please review the reactions we did last session and the one before that, and you should have lots of details about those 3. Look, I almost finished on time. It only took the whole semester. And someone asked me to repeat the gem diol thing again. So yes, for the gem diols, when we have a ketone, we prefer the ketone form over the gem diol form. If we have an aldehyde, we prefer the gem diol form over the aldehyde. And let me send that attendance link one more time. Also, I am a doof sometimes because I completely forgot that we were supposed to have SI today, so I said all my goodbyes on Friday. But you guys were so great. You guys are like my faves. It was such a great semester. I'm sorry 2020 has been so weird, but I hope this was helpful. I hope Orgo 2 wasn't that bad. I think you guys are going to do amazing on the exam. you have any questions, please feel free to email me. And I hope I see you guys on Wednesday. I was going to bring glitter and throw it, but my grandparents said no.